What's up everyone, my name is Nigel Uno, number 1 is my nickname. Today I am endeavouring to teach you all about the IBM quantum experience. Before we get started, you all might know me from the TV show codename Kids Next Door. After saving the world, I went on to Oxford University to study computer science. I worked a little with Lloyds of London in cybersecurity, and now I'm a full-time professor at Meta U. I have 2 daughters and we currently live in Alpharetta, Georgia. With that being said, let us embark on a fun lecture delving into the IBM quantum experience. Quantum computing has been growing in popularity over the past few years, most recently since IBM released the IBM Quantum Experience, IQX, back in May 2016. This release was the first of its kind, hosted on the cloud and providing the world with the opportunity to experiment with a quantum computer for free. The IQX includes a user interface that allows anyone to run experiments on both a simulator and on a real quantum computer. The goal of this lecture is to first introduce you to the IBM Quantum Experience site, specifically the dashboard, which contains everything you need in order to run experiments. It also allows you to experiment with existing experiments contributed by other developers from around the world, the benefits of which can help you to understand how others are experimenting, and you can perhaps collaborate with them if the experiments correlate with your own ideas. This chapter will help you understand what actions and information are available in each view. This includes creating an experiment, running experiments on a simulator or real quantum device, information about your profile, available backends, or pending results to experiments. So, let's get started. The following topics will be covered in this lecture. Navigating the IBM Quantum Experience. Getting started with IBM Quantum Experience, technical requirements. Throughout this lecture, it is expected that you will have some experience in developing with Python, and, although it isn't necessary, some basic knowledge of classical and quantum mechanics would help. Most of the information will be provided with each chapter, so if you do not have knowledge of classical or quantum mechanics, we will cover what you need to know here. For those of you that do have knowledge, the information here will serve as a refresher. The Python editor used throughout this book is Jupyter Notebook. You can of course use any Python editor of your choice. This may include Watson Studio, PyCharm, Spider, Visual Studio Code, and so on. Navigating the IBM Quantum Experience. As mentioned earlier, the dashboard is your high-level view of what you will normally see once you log into IQX. It aggregates multiple views that you can see, and this helps you to get an idea as to what machines you have access to and what experiments you have pending, running, or completed. In this lecture, we will go through the steps to get registered on IQX. Let's do that in the next section, registering to the IBM Quantum Experience. In this section, we will get registered and explain what happens in the background once you sign up to IQX for the first time. This will help you understand what features and configurations are prepared and available to you upon registration. To register to the IBM Quantum Experience, follow these steps. The first step is to head over to the IBM Quantum Experience site at the following link: Quantum Computing, IBM.com. Sign in to your account from the login screen, as shown in Figure 1.1. Your individual situation will determine how to proceed from there. If you already have an account or are already signed in, you can skip this section and move on to the next one. If you have not registered, then you can select the login method of your choice from the sign-in screen. As you can see, you can register using various methods, such as with your IBM ID, Google, GitHub, Twitter, LinkedIn, or by email. If you do not have any of the account types listed, then you can simply register for an IBM ID account and use that to sign in. Figure 1.1. The IBM Quantum Experience sign-in page. Once you select the login method of your choice, you will see the login screen for that method. Simply fill out the information, if it's not already there, and select Login. Once signed in, you will land on the home page. This is the first page you will see each time you log in to the IBM Quantum Experience site. Now that you have registered to the IBM Quantum Experience, let's take a quick tour and delve into some features that make up the IQX homepage. Let's start by reviewing the homepage, specifically the Personal Profile tab. You can access your personal profile via your avatar, located at the top right of the page. Understanding the Personal Profile tab. This section explains the profile of the logged-in user. This is helpful if you have multiple accounts and you wish to keep track of them. Getting started with IBM Quantum Experience. This section provides a quick way to launch either Circuit Composer or the notebooks located in the Quantum Lab views, herein simply referred to as Qiskit notebooks, each of which we will cover in detail in Chapter 2, Circuit Composer, Creating a Quantum Circuit, and Chapter 3, Creating Quantum Circuits. Using Qiskit notebooks, respectively, so hang in there. But as with other views, Know that you can kickstart either from the main dashboard view or from the left panel. Each button easily provides a quick launch for either of the two circuit generators. Learning about your backends. This section lists the available backend quantum systems that are provisioned for your use, as shown in Figure 1.3. It not only provides a list of the available backends, but also provides details for each, such as the status of each backend. The status includes whether the device is online or in maintenance mode, how many qubits, quantum bits, each device contains, and how many experiments are in the queue to be run on the device. It also contains a color bar graph to indicate queue wait times, as illustrated between IBM Q16 Melbourne and IBM Q Rome in the following screenshot. Be aware that the quantum devices listed for you may be different from those listed here. Figure 1.3, provisioned backend simulators and devices. From the preceding screenshot, you can see that another great feature that IQX has with respect to the backend service is the ability to see the hardware details of each real quantum device. If you hover your mouse over each device listed, you will see an expansion icon appear at the top right of the device information block. If you select a device, for example, IBM 16 Melbourne, you will see the device details view appear as shown in the following screenshots. Figure 1.4, device details view. The status, left, and configuration and error rates, right. From the previous screenshot, you can see that the device details view contains some very relevant information, particularly if you are working on any experiments that have intricate connectivity between qubits or analyzing error mitigation techniques. On the left of the screenshot, Figure 1.4, you can see the basic status information of the device. This is similar to what you see before expanding the device information. In the square on the right, we get into a little more detail with respect to the device's configuration, connectivity, and error rates, as described in the shaded bar area, where the error rate rank is illustrated by single qubit U3 error rate and Senot error rate, single qubit and multi-qubit, respectively. Qubits are identified as the circlers where the number specifies the qubit number in the device. The arrows in between identify how each qubit is connected to the other qubits. The connections are specific to how the multi-qubit operations are specified. For example, in the 15-qubit configuration in Figure 1.42 on the right, you can see that qubit number 4 is the source for target qubits 3 and 10. We will get into what source and target mean later, but for now just assume that actions to the target qubit are triggered by the source qubit. You can also see that qubit 4 is the target qubit of qubit 5. This visual representation is based on information provided by the device configuration, which you can also access programmatically using Qiskit. Another piece of information you can get here is the error rates. The devices are calibrated at least once a day or so, and each time they are calibrated, they calculate the average error rates for a single gate, U3, and multi-gates, CNOT. The error rates vary per qubit, or qubits for multi-gates, and therefore, the diagram uses a color heat map to identify where the qubit sits on the error rate scale. Each qubit has a different color associated with it. This color makes it possible to visually identify where on the error rate scale that qubit falls. If you are running an experiment on a qubit that requires low error rates, then you can see from this diagram which of these qubits has the lowest error rate when last calibrated. Below the qubit configuration, you will see a link that also allows you to download the entire configuration information in a spreadsheet. The details there are very specific to each qubit, and they provide more information that isn't visible on the qubit configuration diagram. Finally, at the bottom of the view are the specifics of the device itself, which includes the number of qubits, the date the device went online, and the basis gates available on the device. You can now close the device configuration diagram to return to the dashboard, where we will next learn about the quantum programs and how to monitor them. From the preceding screenshot, you can see that on your account page, you will see the following information sections. Account details. This section has your account and contact information that you use to register. It also includes options such as resetting your password, privacy and security information, and the option to delete your account. Qiskit in IBM Quantum Experience. This includes a quick link to launch a Qiskit notebook to run your experiments. We will review the Qiskit notebook later in this book, but for now just know that you can launch a Qiskit notebook from here as well. Qiskit in local environment. This section allows you to install Qiskit and run experiments from your local machine without the need to connect to IQX via the cloud. This is exceptionally helpful when you wish to run experiments but do not have access to a network. By running experiments from your local machine, this allows you to run simulators that are installed as part of the Qiskit installation. However, keep in mind that in order to run the experiments on a real quantum device, you will need network connectivity to those real devices. If you want to run the experiments on a real device from your local machine, then you will need to copy the token, highlighted in Figure 1.7, that was generated for you in the background. You should then assign it to the Qiskit IBM-Q provider class. Details of the IBM-Q provider class will be discussed in Chapter 9, Executing Circuits using Qiskit AI. But for now, this is where you can copy the Application Programming Interface API token. Also, note that there is an option to regenerate the API token. If you choose to regenerate the token, you will need to delete your old token and save the regenerated one in your local IBM-Q provider class. The save account method of the IBM-Q provider class will persist the value in your local machine, so you will only have to save it once and then load the account each time you wish to use a real quantum device for your experiment. Since this book is written primarily for use on the IBM Quantum Experience site, we will cover running and setting up on your local machine. Just in case you happen to not have network connectivity, you can still run simulated experiments locally. Notification settings. This section simply allows you to set your notifications and how you prefer to receive information, such as when experiments have completed or other information or surveys that you wish to contribute. Your accounts. This last section toward the bottom of the My Account view is an overview of the accounts that you have and a list of the provisioned systems you have access to. These provisions are selected and assigned as part of the sign-up process. This includes information such as when you first signed up, the project that you are associated with, main is usually the default project, provider information, and the allocated backend systems that you have access to. These allocated backends that you can see are either real devices, such as IBM Q16's Melbourne, or simulators, such as IBM Q Chasm Simulator, which are running on the IQX cloud. We will discuss the details of the simulators and devices in later chapters. Now that we are done with our tour of the IBM Quantum Experience layout, we're ready to get to work. In the following chapters, we will delve into each section and progress to writing quantum programs. Summary. In this chapter, we reviewed the dashboard, which provides plenty of information to help you get a good lay of the land. You now know where to find information regarding your profile, details for each of the devices you have available, the status of each device, as well as the status and results of your experiments. Knowing where to find this information will help you monitor your experiments and enable you to understand the state of your experiments by reviewing your back-end services, monitoring queue times, and viewing your results queues. You also have the skills to create an experiment using either Circuit Composer or the Qiskit notebooks. In the next chapter, we will learn about Circuit Composer in detail. Understanding basic quantum computing principles. Quantum computing, particularly its algorithms, leverage three quantum computing principles, namely superposition, entanglement, and interference. In this chapter, we'll review each of these so that we can understand what each provides, the effect it has on each qubit, and how to represent them using the quantum gate sets provided to us. As a bonus, we will also create a quantum teleportation circuit that will leverage two of the three quantum computing principles to teleport an unknown state from one person to another. The following topics will be covered in this chapter: introducing quantum computing, understanding superposition, understanding entanglement, learning about the effects of interference between qubits, creating a quantum teleportation circuit. This chapter will focus on the three main quantum computing principles that will help you better understand how they are used in the various quantum algorithms. The quantum computers hosted on the IBM Quantum Experience leverage all these principles by use of the various quantum gates, some of which you used earlier in this book. Technical requirements. In this chapter, some basic knowledge of programming is required. Some Python development knowledge is preferred as the experiments leverage Python libraries. Some general knowledge of physics is recommended. However, my goal is for the explanations to help you understand the quantum principles without the need for you to register for a physics course or read the Feynman lectures. Quantum computing isn't a subject that is as common as learning algebra or reading some of the literary classics. However, For most scientists and engineers, or any other field that includes studying physics, quantum computing is part of the curriculum. For some of us who don't quite recall our studies in physics, or have never studied it, need not worry, as this section aims to provide you with information that will either refresh your recollection on the topic, or at least perhaps help you understand what each of the principles used in quantum computing mean. Let's start with a general definition of quantum mechanics. Quantum mechanics, as defined by most texts, is the study of nature at its smallest scale. In this case, the subatomic scale. The study of quantum mechanics is not new. Its growth began in the early 1900s by many physicists, whose names still chime in many of the current theories and experiments. The names of such physicists include Erwin Schrödinger, Max Planck, Werner Heisenberg, Max Born, Paul Dirac, and Albert Einstein, among others. As years passed, many other scientists expanded on the foundations of quantum mechanics and began performing experiments that would either prove, disprove, or oftentimes illustrate that there is no proof. One of the more popular experiments is the double-slit experiment. Although this is found in classical mechanics, it is referenced in quantum computing to describe the behavior of a quantum bit, qubit. It is in this experiment researchers were able to demonstrate that light, or photons, can be characterized as both waves and particles. There were many distinct experiments that have been conducted over the years that illustrate this phenomenon, one of which was to fire particles through a double slit one at a time, where at the other side of the double slit was a screen that captured, as a point, the location where each particle would hit. When only one slit was open, all the particles would appear as a stack of points directly in front of the slit. From the previous diagram, you can see that all the particles are captured in an area directly across the slit. However, when the second slit was open, it was imagined that there would be an identical stack of points on the screen. But this was not the case, as what was captured appeared to be a formation altogether different than what would be expected from a particle. In fact, it had the characteristics of a wave in that the points on the screen seemed to display a diffraction pattern, as shown in the following diagram. From the previous diagram, you can see that all the particles are spread out from the center with interference gaps. This diffraction pattern is caused by the interference of the light waves passing through the slits. Here, there are more points at the center of the screen than there are toward the outer ends of the observing screen. This wave-particle phenomenon gave birth to lots of interesting research and development, such as the Copenhagen interpretation, many-worlds interpretation, and the de Broglie-Bohm theory. What this illustrated was that the light appeared as bands of light in certain areas of the board with some probability. By observing the preceding diagram, you can see that there is a higher probability that the electron fired from the gun will land in the center band of the screen as opposed to the outer bands.